Hi, good evening, and welcome to AI Talks Live, a production of the global AI community. My name is Alicia Moniz, and I will be your host tonight. Joining us will be Matthew Guzdial.
Hey.
Welcome, Matthew.
Thanks for having me.
So Matthew is an assistant professor in the computer science department of the University of Alberta. His research focuses on the intersection of machine learning, creativity, and human-centered computing. This includes investigating machine learning-based automated game design, human AI design collaboration, improving machine learning transfer, and generalization with computational creativity and user experience modeling. He is a recipient of a Unity Graduate Fellowship and 2 Best Conference Paper Awards. His work has been featured in the BBC, Wired, Popular Science, and Time. So it sounds amazing, and we're truly grateful to have you here with us as part of the global AI community. So welcome, Matthew.
Hey, thanks.
So tonight you're here to talk to us about creative AI and how AI can generate games.
Yep. What would be good to get us started on then? I can give a little pitch, or we can start on questions, whatever you'd like to
do. Well, before we dive in then, what are some of the things that we should know that most people don't know?
Oh, okay. All right. Ooh, that's a big question. So in terms of, let's see. Let's start with what most people know, or at least some people know, right? So what some people know is that there's this thing called procedural content generation. That's one thing that some people might know. And that some games generate content automatically on the fly as people are playing them, so that each experience is unique. That tends to use standard AI method, often things like constructive grammars, things that were popular in like natural language generation, maybe 20, 15 years ago, something like that. Then on the other side, you might have people who are familiar with deep reinforcement learning and how deep reinforcement learning has been hugely successful in a variety of very public human versus AI game matches recently, from Go to things like the Dota 2 and StarCraft and all kinds of things like that. My research is sort of in between these things, where we're interested in sort of the machine learning stuff, but we're interested in how machine learning can be used to help us make new game content, like in PCG, as traditional PCG typically requires a great deal of human authoring. So you sort of have to be an expert designer and an expert AI developer to be able to use it effectively. So we'd like to lower that barrier, if at all possible, to help lots more people to be able to make more games faster.
That's interesting. And when we were talking earlier, I hadn't realized that there was such an intersection of, the machine learning and the Python with the game design. So that was absolutely something that I hadn't known. So thank you for sharing.
Happy to.
So I'll go ahead and let you get into your presentation. And
sure.
Thank you.
Okay, so we can go over some of this. So let me actually jump a little bit ahead of where we are right now. So I don't think we're going to go through this whole thing, but we can. So this is 80 slides there at the bottom. I don't think we're going to go through 80 slides, but let's get going, see what we want to talk about, and we can take breaks as we're interested in taking breaks. So there's questions or things like that. So this talk is basically 66% the question of how do we make AI or machine learning creative, which we can think of as being sort of a fundamental AI and machine learning problem. And the second bit is sort of harnessing the creativity that we add to an AI ML system for people, which is both an AI ML problem and an HCI problem, right? So we can think about some desired properties we would ideally like to see in machine learning. These might be things like learning well from small amounts of data, The ability to handle novelty and surprise, both in terms of its input and its output. So being able to intelligently respond to things outside of the training set. And the ability to be explainable, especially when it comes to non-experts, as most of the people who are going to be interacting with deployed machine learning systems are not machine learning experts. So I will now propose a related question, shall we say, which is, what does it mean to be creative? Now, this is a fairly controversial question, actually, but I'm going to say that to be creative, you need to be able to generalize well from a few examples, which is like, if I have a small child and I've told them that this dog on the left is a dog, they should be able to figure out that this dog on the right is also a dog, despite the two looking nothing alike. We should be able to produce novel and valuable work in comparison to prior work. So the sort of famous example here is the invention of French fries, which is sort of this invention of a new thing entirely out of sort of constraints of something old, and the ability to explain your work. So many creative people, particularly artists, have to explain their work through things like artist statements, talking about their work through criticism, these kinds of things. So these are the kinds of features that I'm fairly clearly making a parallel to the kinds of features we would like to see in machine learning systems. So that leads naturally to a few research questions that I pursue in my work. So these are things like, in terms of making AI ML creative, the first sort of section there, how do we apply machine learning to creative domains? That's not as obvious as it might sound, as creative domains have all these interesting little quirks to them, like having relatively small amounts of training data and being very varied versus a lot of things that we would typically apply machine learning to. And how do we get machine learning to produce truly novel output? So not just sampling near the average or the median of a distribution, how do we get it to produce things that are entirely novel from things we've seen before? And then in terms of this third question, which has to do with harnessing the creativity for people, how do we make sure this creative machine learning can work for people? Which gets us to this notion of making AI and ML creative. Now for this, and I think it's helpful for this conversation, I'm going to define a little bit of a creativity framework. Now this is also a little bit controversial, but it'll work for the purposes of this talk and for the purposes of this conversation. So we're going to call creativity 0, or creativity level 0, is just mimicry. You tell me exactly what to do and I do it, right? Even if this leads to a creative action, a wildly interesting novel that you dictated, I'm not doing any of the creativity myself, right? The system itself has no creativity. The human who told the system what to do has the creativity. And we have creativity 1, which is mimicry, but then a little bit of variation. So we can think of this like a GAN, which is going to be trained on a generative adversarial neural network, in case you're not familiar, can be trained on lots and lots of faces, can produce new faces, which are variations, can be thought of as variations on the faces it's seen already. But it doesn't matter how many images of human faces we've been trained on. I'm never going to produce, the face of a cat unless I've been trained on the face of a cat, right? Then we have what I'm going to call creativity level 2, which is going to be novelty within a genre or domain. So it's going to be a new example of something within a genre or domain. So if this was writing, it might be a new book, a new story. If this was games, it might be a brand new game, music, a brand new song, things like that. Then we have creativity 3, which is genre or domain defining novelty. So this is the invention of a thing which creates a new genre or domain by its existence. That's obviously the goal, and I'm not going to suggest that we're there yet, but that's sort of what my research works towards. So the problem domains that I'm interested in are sort of two major ones, or as far we're going to talk about today. So the first one is video game design, and I'll argue as to why that's interesting in a second. And the second is image classification, which might seem entirely different, but there's a link, trust me. So in terms of video games as a domain, video games are a challenge for standard applications of machine learning for a few reasons. One, they're an interactive piece of software composed of both game rules and design structure that you navigate. Because of this, we have a sort of a weird representation question. They're literally a piece of software. They're made up of rules and structure, right? there's not an easy mapping to think, oh, this is just a natural language problem, or oh, this is just an image processing problem. They're really distinct. There's a hugely wide variance from game to game, even within a particular title, within a particular series. You'll have a crazy amount of variance from each game. There's also not that many of them. And that leads to this question of, what do you use as input to a machine learning process? And notably, if we can get this sort of creativity 3 for AI and machine learning working for video games as a domain, then there's all kinds of applications in entertainment. Obviously, that one's fairly straightforward, but also in terms of education and things like that. So we can think about, okay, can we decrease development time for game-based learning, right? Can we help teachers to make specialized games to teach specific subjects to their particular classes, right? So these are the kinds of things we can do if we solve this problem. So let's take the framework from earlier and then put this into the context of games. So creativity 1 for games. What does this look like? Well, this sort of touches on this research question 1 of, how do we apply machine learning to creative domains? Well, what I'm going to say that we'd want to do to hit creativity 1, which as a reminder was mimicry plus a little bit of variation, we're going to want to learn a model of rules, learn a model of the level structure, the sort of 2 pieces of a game that I identified earlier, and then combine these things together, which would give you a clone or a hack of a game. For example, we might pick Super Mario Brothers. So I'm going to jump ahead a little bit. We can jump back into this if we want. I should talk about gameplay video. So one of the things we use as input in this process is gameplay video, as opposed to, say, the game software, which has a number of benefits. So there's a big existing corpora on YouTube and Twitch. People are constantly streaming games. It contains character element interactions. If I have a piece of software, that doesn't tell me how to play it or interact with it. But if I have video, I see how people interact with the software. And I'm sort of making the argument, it has everything we need to fully recreate a game. So what I end up doing for this work, this is all existing prior published work, is we took output gameplay video, we separately learned game rules and game level design, and then we had a combined representation at the end. I'm going to jump ahead a little bit here. So for rule learning, this was based on a paper out of IJKAI in 2017, Game Engine Learning from Video, where we're basically restructuring this problem by re-representing pixels, the raw pixels, as symbols, as symbolic facts-based representation. And then we are learning rules, learning literal if-then rules via a standard search optimization problem. And that's leading to some pretty interesting output. So let's see if we can go ahead and play from this current slide. So on the right side here, we have original video of somebody playing Super Mario Brothers and Mega Man. Both of these videos just taken off of YouTube. On the left, we have the recreation, the learned recreation of these games from the learned rules. Now, you'll note they're not perfect. There's all kinds of weird stuff going on, like Mega Man, these weird pipes are wiggling. It sometimes has things disappear. But overall, it's pretty darn good. And notably, this is trained on only 2, I believe, each one was only 2-minute video, so 4 minutes of footage in total, which is just drastically small versus most machine learning approaches. So we've learned some rules. Notably, we did a reinforcement learning inspired evaluation. We can jump back to that in a bit if people are interested. But the second bit that we had to learn was the level design. So first was game rules, then level design. For level design, we actually structured this as a Bayesian unsupervised learning process, which might be surprising to people who think that the only kind of networks they care about are neural ones. But Bayesian networks are actually still very, very good at learning sort of component relationships in 3D and 2D shapes. So we represented this as a Bayesian network where we had these particular nodes. The blue nodes are going to be nodes which are observed values. The white nodes are going to be hidden values. And these arrows indicate a sort of dependency in terms of the probability distribution of each node. So this allowed us to capture things like the geometric information for shapes of sprites that occur on a screen, like this sort of rectangle of question mark blocks, the relationships between these sprite shapes, the counts of these sprites, the styles of sprite shapes. Now, notably, these are white nodes here, which means we have to automatically learn them, which we learn via k-means clustering with k estimated to be the distortion ratio, these different categories, which give you different types of sprite shapes that might occur on the left side of the screen, these taller blocks here, or at the top of the screen, these wider blocks here. And then we have these L nodes, which represent chunks of level style. And then we can basically string these L nodes together to create whole new levels. And we ran a human subject study, and it did an extremely good job of matching sort of how humans go about understanding video game level design. So I'm going to jump here again. So we've done both of these two things, and then we have this combined representation. We call this combined representation a game graph. For that, we take a sprite sheet, which is basically a listing of all of the entities of a game. Here it is for Super Mario Brothers. We take all of our information, the rule information and the level design information. We have those represented as edges. And that gives us, this is a tiny little subset, but this gives us something like this, where each image is a node and each edge has a particular kind of game design knowledge on it. But this only gets us to creativity 1, which was mimicry plus a little bit of variation. And that gets us to the second research question. How do we get machine learning to produce truly novel output? Okay, so let me pause there for just a second, because I just went over a whole bunch of stuff. And let's see if there's any questions, anything going on. Should I pause and explain anything in more detail here? Or do you think we're all right? I'm not hearing you if you're speaking. Oh.
No questions from the stream. Thank you, Matthew.
All right. Yeah, no worries at all. Okay, so in that case, let's jump back into here. Okay, so what we just did was we cloned Super Mario Brothers 1. We were able to produce all the rules of the game, be able to produce new levels of the game. It's just basically more of Super Mario Brothers 1. But there's a question here: how do we go about making a new Super Mario Brothers game, which would give us to creativity 2, which, as a reminder, was a new instance, a new particular example of a particular genre or domain. So an example here might be Super Mario Brothers 2. So in Super Mario Brothers 2, they had all the same mechanics of the original game, but they have new kinds of levels that couldn't have existed in the original game. So that seems like a good place to start. For example, we might say we want something like an underwater castle. Now, this is a kind of level that does not exist in the original Super Mario Brothers. You have, this underwater level, but with all of these sort of castle blocks. You have bars going up and down, and you have a Bowser here at the end. Bowser's the enemy in Mario. Notably, this is from a paper, Learning to Blend Computer Game Levels from ICCC 2016 that won a Best Paper Award. So, spoiler alert, this is what we were able to do automatically through this process I'm about to introduce. But let me actually introduce it. So there's all kinds of different ways of representing creativity, right? There's lots of ways of measuring creativity. And there's lots of ways of doing actions we might think of as being creative. One of these is referred to as combinational creativity. This is the cognitive process that you or I do when we recombine old knowledge to make something new. The easy example here is if I tell you to come up with a new animal, right? If I just say, come up with a new animal, this is an animal that has not existed ever before. Almost always what you're going to do is you are going to imagine one existing animal, let's say like a dog or something, with the traits of another animal or with some combination from another existing animal. It's a really easy way that humans have to produce new things by combining old knowledge, but computers aren't very good at it. Now, there are a few functions for trying to represent this. For example, there's conceptual blending. So let me give you an example of how conceptual blending works. So over here on the left, we have one piece of input. This is a little graph, right? This sort of V-shaped graph, where each of the nodes is a thing, and each of the edges is a relationship between these things. So input 1 would be read as a resident who lives in a house on the land. So it's basically the idea of living in a house. And input 2 would be a passenger that rides a boat on the water. So the idea of riding on a boat. With conceptual blending, which is a particular way of combining concepts, doing combinational creativity, a particular function for doing that, you would end up getting as output a resident passenger rides/lives in a houseboat on the water. So conceptual expansion has sort of invented the notion of a houseboat from these two inputs. So that's interesting, right? That seems very powerful. But there's a few drawbacks. Conceptual blending almost always requires human-authored input, nicely formatted human-authored input to work, right? So that it can figure out what are the same things that should be combined together. As you can see in this example, where I literally have the three graphs have exactly the same shape. But you know what? Why don't we try it? And spoiler alert, we did try it and it worked. But what if we tried it with these level design models that I mentioned just a second ago? So these are two different L nodes. It's two different of these probabilistic graphical models representing two different kinds of levels. This one on the top left here, which is sort of an above ground Mario level, and this one over here, which represents like a castle or a boss level. So those are input 1 and 2. But there's a small problem. These graphs are way more complicated than these little V-shaped graphs I showed you before. So we're actually going to simplify them. And we simplify them by basically taking the S nodes, which, as a reminder, were the styles of sprite shapes. And we look at the minimum number of most probable connections needed to connect all the S nodes together. And that gives us these much nicer, more abstract, higher level graphs that still contain all the information you need to understand this kind of level. We're then just going to run conceptual blending on this nice simplified graph, convert it back into our actual representation, our actual L node representation, and then we can use that to generate whole new levels. Simply said, we can make underwater castles. This is an example of a level produced entirely by an AI through this conceptual blending process. Take a drink of water. Okay, but there's a problem. So I already mentioned earlier that this approach to doing creativity this approach to producing new things is constrained. It's constrained in a few ways. Obviously, I mentioned that it tends to need well-shaped or well-formatted human-authored input. There's a few other things as well. So if we can imagine we have two inputs. Let's call them M1 and M2. I'm going to say M1 and M2 because we're now going to be dealing with machine-learned information. We can sort of imagine the possible ways we might combine these two things together. So what conceptual blending does, it's these sort of B circles over here and over here. It lets you sort of extrapolate off of your pieces of input to sort of represent things in this sort of conceptual space. And then there's other, as I mentioned, other approaches for combinational creativity. For example, Santiago Antonon's amalgamation, which allows you to interpolate between things, and compositional adaptation, which lets you change in model complexity. But what if I wanted to query what was up here, or over here, or over here? Or even worse, what if I had more than two pieces of input, which seems reasonable. After all, there's been more than 2 games that have ever been made. None of these approaches can handle more than one example of input simultaneously by default. So what do we do? Well, I just introduced this to you as a space. And if it's a space, that means that we should be able to come up with a function that will let us query an arbitrary point in this space. So that's what we did. So what we did was we took example game graphs. Here's one for Super Mario Brothers. Here's one for Kirby. And here's a third one that we also learned for Mega Man, the first Mega Man game. And we came up with a function which allowed us to query arbitrary points in a space defined by the possible combinations of these games. And that function is called conceptual expansion. So I have sort of the simple version of it up above and then a more complicated version of it below. But we'll sort of go through both using them to reinforce one another. So a conceptual expansion that targets a particular concept X, which in this case would be this sort of duck-faced looking smiley over here on the right, takes in a set of features, existing features. In this case, it'd be these sort of bitwise looking smileys over here. And then it takes in a set of what we call alpha masks or alpha filters. And these would be these sort of big rectangles over here. And what is happening here is that each one of these masks is acting as an instruction to say, what do we take of each of these filters, or each of these filters and features. So for example, right here, we're going to be taking the sort of mouth area and the eyes of this smiley face. We're going to take this sort of middle section here of this smiley face, and we're going to take the sort of outer section here of this smiley face. Put it all together, and you get this representation here. So by changing, these act as our parameters. So by changing the values of these alpha features, telling us what do we grab, and the features values that we're grabbing, we can sort of explore the fullness of all possible combinations over an arbitrary number of inputs. Which means that I can query, say, this point right here. And we can take a look and we can say, oh, hey, this is a game. Every point in the space is a game. It's a combination of these games. And this game might be a fairly standard looking platformer. So we can query another point in the space. If we vary things a little bit, we can go to the neighbors. This is just standard search, right? And here, this might be a more interesting game level, but there's no player anymore. So we search again, and now we find something quite interesting. And then say we take what was, a whole bunch of Python code, and we write a little script to convert it into a C# thing so we can put it in Unity and play it, and we get this. So here's an example of me playing a game where all of the rules of the game and all of the level structure of the game was automatically created via these machine learned models via this conceptual expansion recombination approach. So what's happening here, right, is I'm controlling this little blue thing. And every time I jump on anything, it's being destroyed. Now, when I showed this to Mike Cook, who's an expert in both procedural content generation and creativity, when I showed it to him, he said, oh, it looks like you recombine Super Mario Brothers and Breakout, or Brick Break, that game where you sort of have a little ball and it hits bricks and they explode. But that's not what happened. I just told you, right? We combined Super Mario Brothers, Kirby, and Mega Man to create this game. So what's actually happening here is that the concept of level structure across these three games and the concept of an enemy, particularly the Goomba enemy from Super Mario Brothers, has been combined, which is leading to this rule where every time I hit anything, I'm destroying it, which leads to this really interesting and novel little game, right? I don't think it's, revolutionary or anything, but it's definitely distinct from any of the inputs. And then, of course, the rest of this process is basically filling in the gaps of like what kind of level structure you might want and things like that from that. Okay, so some takeaways, right? To the best of my knowledge, this is now past tense, this is from 2019, so it's old school. This represented the first machine learning-based automated game designer. And with conceptual expansion and from just a few inputs, we can produce novel output. So at this point, you might be asking yourself, okay, so where are we in the framework? We have creativity 0 was mimicry, as a reminder, then mimicry plus variation. So we definitely at least have hit creativity 2, which was novelty within a genre or domain. But I don't think we've definitely hit genre or domain defining novelty. We haven't produced anything that's like, an epoch defining game or anything like that. So I'm going to be kind to myself, though, and say that we're 2.5. It's a little twist on existing work, just as I've twisted this framework to fit my needs. But at the top of this, I told you this isn't just games, and that's true because we also have tried this in image classification. So I'm going to take another second here, get a drink of water, see if any questions pop up in the chat, and then we'll move on to this. Okay, I now also have the YouTube video open, so I can see there's nothing yet in the chat. So I'm going to assume no questions at this point. Oh, I guess I'm a little delayed, though. Oh, you're muted, I think.
No questions at this point. Thank you, Matthew.
Cool. Okay, so let's jump into the non-game portion of this. Okay, so let's imagine a toy problem, right? A new animal has been discovered. Now, of course, this is a fairly silly toy example, but let's just hold with it. Let's say that this new animal is a little bit like a cat and a little bit like a dog. And when we see it, we spot this animal for the first time, we decide, I don't know, let's call it something like fox. Now, let's say that this new animal, we wanted to come up with an image classifier, a neural network well, anything, let me not jump ahead of myself, an image classification approach, an automated computer image classification approach. So if this weird animal called a fox ever showed up again, we would be able to recognize it. So the problem here is that the most common way to do an image classifier these days is to use a deep neural network. And deep neural networks, while being the state of the art in image recognition, require a large amount of data. And if we've just discovered this animal, there's no guarantee we have all that much data. So what do? Now, there is this thing where deep neural networks have a nice graph or matrix-like knowledge representation. And I just showed you the ability to recombine things that have a nice graph or matrix-like knowledge representation. So what if we recombined a neural network? So that's the idea here. We're going to run our conceptual expansion approach in deep neural networks to be able to recombine the existing knowledge in the neural network to be able to approximate a deep neural network for entirely new things. So for example, we did conceptual expansion of image classification models. Specifically, what we did was we trained a network on CFAR10, which represents the classes airplane, automobile, bird, cat, deer, dog, frog, horse, ship, truck, etc. And then we introduced new things like foxes. Notably, this is taken from, this is not true anymore. This is published and has a best paper award. Ignore that under review. This is also at ICCC. So this is from our paper, Combinates, Learning New Models via Recombination. So I'm not going to go through the whole thing. I've already been talking for like 30 minutes, but let's talk about this results summary that we got. So when we were trying to do this problem of going from N, the original 10 classes from CFARNet, to N plus 1, introducing things like foxes or planes or Pegasus, etc., we also tried to go from CFAR10 all the way to CFAR100, which is 100 new image classes. So going from the 10 I told you to 100 new ones. And in all cases, we beat out transfer learning and zero-shot baselines, standard ones that didn't require any extra knowledge or information, by roughly 3 to 30% accuracy, with an average of roughly 10% accuracy beating out these existing approaches. And this is notably on hyper low levels of data. So this is like 5 to 10 to going all the way up to 500 examples of new classes, of new images. So big takeaway, this isn't just games. So at the top of this, I told you that our goal was creative AI or machine learning. I showed you creativity 0, which is just pure mimicry in terms of rule learning. I showed you creativity 1 in terms of being able to replicate the existing levels of Super Mario Brothers and then some variation. I showed you something closer to creativity 2 in terms of this game graph, which was a sort of rough approximation of the original Super Mario Brothers. I showed you an example of a brand new kind of game level that hadn't existed before, and it's an example of creativity 2. And I showed you a new kind of game that had never existed before as an example of creativity 2.5. And with Combinates, the conceptual expansion over deep neural networks. So that brings me to the last question that we have here of how do we make this creative machine learning work for people? So we're not a creativity 3, but I do think there's some value here. And I think I have, shown some evidence to back that up, that there's some value to this approach so far. So how do we apply this to people? I sort of pitched this at the top as being better for working with people. How do we do that? This is an open research area, and there's many possible questions. What kind of AI should we use? What kind of interface do we use, et cetera, et cetera? One simple way to think about this is, if I'm going to make an AI to help a chef, does the AI go in the spoon, or is the AI a whole other robot chef to help the chef, right? Big questions. So to start with, we're going to go with co-creative level design. Co-creative meaning a human and AI working together. And we're going to go with level design because honestly, when we started this was what we'd accomplished so far is this sort of AI level design stuff with machine learning. Notably, this work is published in this paper here, which is published in CHI, the Human AI Conference, or Human, not AI, but Human Computer Interaction Conference in 2019. So there's some questions here. Notably, I put driving questions slide. Well done, Matthew. There's some questions here when we first created this tool. Will users want to engage with an AI partner? What kind of AI partner are users going to prefer? And what kinds of interaction paradigms are best going to support a user's creativity? So our initial level editor was built inside Unity for the game Super Mario Brothers. We had 3 existing machine learning systems as the backend AI. These were the Markov chain, which was by Snodgrass and Antonon, an LSTM, a long short-term memory recurrent neural network, so a deep neural network by Somerville and Matias, and the Bayesian approach that I mentioned earlier. And then we used a turn-based framework. So let me give an example of that. Let me play this video. So this is me working in this tool. So I'm controlling this going back and forth. I've just added these 2 little ground pieces right here. And now I'm going to press this end turn button over here. When I hit that button, that's prompting the Bayesian network in the background to give some addition. So in this case, it's going to add these bricks up along top here. It's fairly slow, so let's jump ahead a little bit. If I add some more ground and some more ground, and I hit this end turn button, and some more ground, come on. And I hit this end turn button again, it again prompts the AI partner to make some addition, in this case, adding some more ground. Okay, so that was the start, the very first setup that we did for this tool. In an exploratory study we ran with novice designers, we basically used 84 undergraduate students. And what we found is that there was almost no significance in differences between the agents overall. Basically, taken in aggregate, people just didn't care which AI was working with them. It was roughly the same for them. At the top here, I have an example of the Markov chain, of a person working with the Markov chain to design 2 levels. And then in the middle, the Bayesian network, and then at the bottom, the LSTM. Now, you might be able to pick apart some differences here, like the BayesNet handles decoration better. The Markov chain has kind of noise that you might expect. The LSTM either sort of does an okay job or has noise like you would expect from these approaches, but overall, these are not hugely different, right? But looking at the data, we found something interesting. Even though there weren't significant differences in terms of how people took these agents overall, there were individual strong preferences. So individuals would still say, oh, I loved the LSTM, or oh, I hated the Markov chain, or conversely, I loved the Markov chain, I hated the BayesNet. Right? But there wasn't one that sort of stood out above the others. So what we took from this was that users vary too much for a single agent. So our idea was, what if instead we used deep reinforcement learning to be able to learn a generalized model and then had to be an active learning agent? So all of those 3 agents in the past for the first round were static. They'd been trained. We were holding out the weights, so they weren't going to be doing any more training. But what we can do is we could learn a general model, which we could then have it specialize to a particular user during the interaction. Okay, so that was one idea. The second thing that we thought was that users grew frustrated deleting the AI's additions, so we added an undo button, and users expressed alarm at some of the AI additions, so we added an explainable AI on the server side. So we then ran a study, made all these changes, and we ran a study with 14 published designers. And these were the results. Designers actually found value in the AI. Designers took inspiration from the AI, and designers' desired role for the AI, however, still varied wildly. So here again are three pairs of output levels. Each one of these pairs, so this top one was by one designer, this middle one was by another designer, this bottom one was by a third designer. And it was all 3 with this deep reinforcement learner. And what I think you can see here pretty clearly is that the top, the middle, and the bottom all have a distinct sense of design to them, right? You can tell these are different. Now, this might be due to the fact that they were all published game designers at this point, but at least the deep reinforcement learning isn't getting in the way. We even had some interesting quotes. So here's a sequence of quotes from an indie video game designer who first said, okay, so I still don't feel quite inspired working with this tool. I'm going to try a tighter feedback loop, by which they meant I'm going to basically hit the end turn button more frequently. They hit the button, got a response from the AI and said, wait, that was nice. Hit the button, got a response from the AI and said, not great, except this part is really great. Hit the end turn button, got a response by the AI and said, honestly, good job, AI. Which is great, right? You can see this sort of the AI getting better across this sequence here. Now, notably, I should have a video. How annoying. I should have had a video in here of me working with the deep reinforcement learner. Let's see if I can find that real quick. I think that's worth digging around in my files a little bit for. Yeah, I think this one might have it. We're just going to go through every single one of my presentations. Here we go. Okay. Let's see. Let me make sure that this is visible. If I look over here, is it showing the right thing? No, it's not. So I'm going to have to stop the screen sharing, share the screen, application window. There we go. Okay, here we go. All right, so let's take a look at what this deep reinforcement learner looked like. There we go. So again, we're going to start exactly the same. I'm going to add some ground at the bottom left. I'm going to hit the end turn button again. So this is the deep reinforcement learner's first suggestion. It adds some bricks up here along the top of the screen. By keeping its suggestion, it turns out adding bricks is a good first move. By keeping its suggestion, as I do here, all those blocks along the top, I'm giving it positive reinforcement. So I'm saying, hey, that was good. So keep on going. I add some more ground along the bottom here. What I'm trying to do is I'm trying to see how long it's going to take the AI to learn a very particular pattern. So I'm going to see how long it takes it to learn this. So getting a response from it again, it added some more bricks. It figured out I liked those, but now it added a stair up here at the top left. That's no good. So let's give it a second example. Now we're on to number two, our second example of this little local pattern of the sort of ground and the two stairs and the pipe. And then I'm going to add piranha plants up here at the top just because, who knows. So I'm going to go ahead and hit the enter button again. This time it added that stair there at the bottom. That's not good. Let's give a third example over here. Oh, I actually only give a partial example at this point. Hit the enter button again. Okay. So this is with roughly only like, let's call it 2.5 examples, and it's already very close, right? We have, this it's sort of filled in these gaps. It has this plant here slightly incorrect, but it's gotten dang close with only 2.5 examples. Now that is way faster than most deep reinforcement learners take in terms of their sample size, right? So what I do here is I go ahead and I finish out that third example. And then I'm going to hit the enter button again. Let's see what it does. So I give it a big negative reward there, right? It gave it a large amount of negative reward, a large amount of punishment for deleting all that. So it gives me almost nothing for this next one. I give it a partial fourth one, and then it does this. Okay, so lots more bricks, but let's go back over here. So, okay, now this is interesting, right? So we have, oh, okay, my mouse disappeared. Whoop. Okay, there we go. So we have this example here, right? Of, oh, did I totally lose the window? I totally lost the window. Where did it even go? It's not that. It's this. Okay, there we go. Okay. Here, let me try to jump to it. No, this is way too late on. So what it's gotten here is in roughly, here we go. So in roughly only 3 and a bit examples, it learned all of these local relationships. So it added this pipe right here. It added this plant, it added this pipe, and it added the ground beneath it. It learned all of those local relationships in only 3 and a bit examples. If we think about it, that makes sense because basically what's going on here is that this is acting as an example of transfer learning, right? We have all this knowledge where this deep reinforcement learner is trained on all these interactions with all these other people, these 84 examples from the first study, and then it's sort of specializing on the fly to a particular person. And that's letting it learn very, very quickly. Okay, so let's jump back over to here. So actually, I think we can go ahead and just call it there for this stuff. Let me go back over here. Here we go. Okay, so I'm going to head and stop sharing the screen for now. But so that gets you the sort of a taste of where my research was. All that published stuff was roughly by the end of 2019. So lots of new stuff that's sort of the next steps for all of these research areas, but that gives you the rough picture.
So that was great. Thank you, Matthew.
You're welcome.
Yeah. So we were talking a little earlier, and it's pretty great how many different publications that you've been featured in and the different articles that you're contributing to across the world. What are some of the topics that journalists are asking you about?
Sure. So recently I've had a number of people asking me about sort of two major things. One is sort of the future of AI in games. So I think this is largely prompted by all the very public examples of, AI beating humans at games recently. And because of that, there's a lot of people sort of understandably asking, okay, so when is this technology coming to, games that you or I might play or other people might play? And the real answer is that it's not. So all of these approaches, all these big successes are based on largely deep reinforcement learning, some Monte Carlo tree search stuff and some other specialized things, but that's basically it. And all of these approaches require a massive amount of training time. For the Dota 2 example, the Dota 2 agent, the OpenAI 5, they trained it, because they trained it in parallel, for more time than the human race has been in existence. Right? Done in parallel, right? So that you could actually do that within, a span of a few months.
Yeah.
That's just wild, right? Nobody except the biggest AI companies can possibly do that. And there are approaches, there are people who are working on things like the Unity ML agents to help everyday designers put deep reinforcement learning in their games. But the real answer is that you can't get that super complicated, fun stuff without massive amounts of computation power. And so people just don't have access to that. But even if we could solve that problem, let's say easy, more computation than the human race has been along before, we're just going to solve that problem automatically. If we could do that, we then run into this problem where deep reinforcement learning agents tend to be extremely, extremely good at learning to meet whatever reward function they're given. But that doesn't necessarily mean that they're going to learn to play a game like a person would. So in the Go example, the famous Go example where the Go AlphaGo was able to beat, the grandmaster at the time, Go took moves that it took months for people to understand why those were good moves. That there were moves there was the traditional understanding of the game would suggest these were bad moves. And so they were moves that allowed us to learn about the game, but in the moment they looked weird. And the same thing happened with OpenAI 5, where OpenAI 5 would constantly take actions that seemed to have no meaning whatsoever. Now, maybe they had some secret meaning that we just don't understand yet, but it could also be that they were just actions that were neither rewarded nor punished. And so because of that, the AI learned, well, I might as well just do these over and over and over again. But that doesn't cause the AI to learn to act like a person would expect the AI should act. And because of that, especially in like big budget industry games where if your AI isn't acting like it should, people are going to get very angry and not buy your game anymore. People just do not want to go through that risk, right? Yeah. They can't afford to experiment like that. Now, there are interesting sort of alternatives there. So there's a recent indie game called Lab Assistant by Liz Fiacco, where you, the player, train an AI to be your lab assistant in a little science lab and do experiments with you, little virtual science lab. And the idea there is it's sort of you're training this thing to understand a language. And it's this small, weird game, and it's sort of buggy and weird, but it's an example of ways that you could try to integrate that. But in these big budget games, no, you wouldn't want the weird stuff to be occurring. But the other thing is that it has been tried. So there was a talk, I'm going to forget his name, but the head, one of the AI leads at EA, Entertainment Arts, for the Gears of War series, they actually talked about, they tried deep reinforcement learning for some of their enemy AI, and they found that it was pretty good, except then they changed one thing in the game, and the AI totally broke. It was extremely brittle, right? It was extremely focused on these little tiny features, right? And those being in a particular way. And because of that, they couldn't make any updates to the game, right? And if we think about making a game, you sort of need to have the whole game ready in a state and then make iterative changes to improvement. But if we need to make the whole game, then train the AI, then make a little change, then retrain the AI, then make a little change, then retrain the AI, it's just way too much effort. So that's one big thing of why aren't we seeing all of these cool new fancy PR stunts showing up in industry games. Another thing that people often ask is, okay, so you're showing that we can automatically generate brand new games, right? So, you know, are we going to be putting game developers out of work, right? It's an understandable question, but I don't think it's particularly one that has a serious chance of happening. There's two big reasons for that. First of all, I've shown that I'm really interested in building AI that works with people, not autonomously away from people. The second one is that as long as it's people who are the primary players of games, you're going to need a person to be the primary designer of games. And you might end up with AI tools that help that person to make games faster or better or more easily testable, things like that. But you're not going to see people outside of the game design process anytime soon.
That makes sense. And it's a common question. I think when people talk about leveraging AI within existing work processes, there's a lot of question about that. And I always bring up like the 80-20 rule. It's, you know, we're hoping to automate some of these 80% tasks that, you know, we spend that 80% of our time on, but have that 20% value, right?
Right.
So that's interesting there. Okay. And we were talking earlier, and one of the benefits of working in academia is that you do get to choose your projects.
Mm-hmm.
So tell me, what types of projects are you working on right now?
Sure. So as I mentioned, we can sort of think of them as like extensions of the work that I just presented. So going further with this sort of conceptual explanation over deep neural networks, the big thing that we're interested in is sort of how far can we push this? So I showed that it worked for image classification. We've actually shown that it works for image generation, at least better than other transfer learning approaches. We're still not perfect there. We can't learn an example of an image generator for foxes from 10 examples. Not yet. But there's this question of where else can this work? Is this just something that works in images? So far, that doesn't seem to be the case. We've got some interesting work with some companies that I can't talk about, but some other work that's in like natural language processing. So it can show that we can learn to recognize new kinds of statements much faster by using conceptual expansion than you could if you were just sort of training from scratch using your available data. You can learn a better model faster. So that's sort of one area of work, lots of stuff going on in there. The other one is sort of, it's sort of this marriage of the first and the last thing we talked about of sort of automated game design and this like co-creative level design interface. Or we're currently working on a co-creative game design interface to allow a person without any coding to, with an AI, produce all the mechanics, all the rules, all the code needed to make their game work. So we should be running user studies on that pretty soon. Fingers crossed.
Okay, well, it sounds exciting, and we'll definitely be glad to hear an update when you've published your new findings on that. It's been a pleasure, and I loved the presentation. So definitely thank you for spending the time with us. Huge thank you from the global AI community. And the video will be available on our YouTube channel at globalai.community/channel. So thank you everyone for joining us tonight.
Thanks for having me.
And until next time.
Bye.
Bye.